Welcome to this decarbonization showcase hosted by NYSERDA's Empire Building Challenge. Its purpose is to familiarize you with technologies and strategies to facilitate decarbonizing our building stock. All sessions will be recorded and posted to the EBC Showcase Series website. Each presentation will be 20 minutes, followed by 10 minutes of Q&A in which your presenter will respond to your questions and which you can post in the webinar chat. And now it is my pleasure to introduce Barry Stevens of Ventacity.
Thank you very much, Sal. It's great to be here. This will be a very quick overview of very high efficiency ventilation. And in the electrification decarbonization world, ventilation is kind of the forgotten stepchild, and a lot of people don't have an appreciation for the importance of the ventilation component. But I think when we get done, you'll realize that it can really have a big impact. Ventacity has been working with some energy efficiency organizations across the country since about 2016. So we've done many projects. I'll share a little data and just give you a little insight into what the ventilation component really means on the HVAC whole system upgrades and retrofits of buildings to reach electrification decarbonization. Passive House certified is something we are proud of, and we were the first commercial ERVs Passive House certified. There are a lot of commercial HRVs, larger capacity units, that were certified, but we were the first ERVs. This is a very high bar to get over, so it's very high net recovery efficiency of how much energy you're recovering, but it's also fan efficiency, how much power you're using. We're going to talk about COP, coefficient of performance. That plays a big part of that. It's also important not to have cross-flow contamination, and the sound level. When you build really efficient buildings and you have tight, well-insulated envelopes, sound levels become a factor, so that's important as well. To give you just a little bit of insight, conventional efficiency, 65 to 70% recovery efficiency, that's normal. And if on a 40-degree day, what we're showing here is a 70 degrees inside temperature, 40 degrees outside. At 65% recovery, you're bringing in 59.5 degrees. At 85% efficiency, you're bringing in 65.5 degrees. So that's a huge difference from comfort level. From an energy perspective, that's where it really gets interesting. The amount of energy to take, in this case, 500 CFM, which would be a single classroom or a modest-sized office, from that 59.5 degrees up to 70 degrees at 65% recovery on the left, we're showing 5,667 BTUs an hour. That 20% difference in recovery efficiency translates into almost 150% difference in energy. So rather than 5,600 BTUs an hour for that classroom, say, we're looking at 2,400 BTUs an hour. So you're having to use a much smaller heating and cooling system in a building that has that very high efficiency ventilation. We do this with a counterflow heat exchanger. They're the most efficient way to transfer energy. It's got more time for the energy to transfer as it goes through that heat exchanger than either wheels or cross-flow heat exchangers. So counterflow is the secret. And what we're looking at here, if you're familiar with COP or coefficient of performance, most people are familiar with heat pumps, which have a coefficient of performance of, say, 3 on an average, 3.5. What that means is 1 watt of energy in gives you 3 or 3.5 watts of heating or cooling out of that heat pump. With electric resistance heat, you put 1 watt into an electric baseboard, and you get 1 watt of heating. It's a COP of 1. So what we're looking at here is our fans are using very low energy, and the recovered energy is very high. So you have the COPs of up to 20 at design temperature here in the summertime, up to 33 in the wintertime. We've seen it even higher in extreme temperature differences. The higher the temperature differential, generally the more energy you're recovering. We looked at a project. We looked at a project near Seattle. It was a school. This was during COVID. And on your left, the competitors, HRVs in this case, they couldn't get them for about 50 weeks. And so the project was going to be not able to be completed in the summer when they wanted to. They contacted us. We were able to deliver them 6 3,000 CFM HRVs in time for their project, but it added cost to the project to do the higher efficiency HRVs. So they had to go to the school board and justify it. So we did an analysis. You can see right at the top, it's fairly small print, but I'll just hit you the highlights here. The fan power, conventional HRVs was over 6,000 watts. The very high efficiency, we were at 3,400. Almost half as much power consumption. And then the heat recovered per month, you look at the difference there, and it's a fairly, not huge, but significant enough difference. What that translated into was a COP of 5 versus a COP of 10.2. The bottom line here is this very high efficiency HRVs were using about half as much energy to provide the ventilation for this school. If you then go down into the chart, we were looking at 15 cents a kilowatt hour in Seattle at the time. And that translated into, over the period of, we rolled that out over 10 years, which was how long they were going to borrow the money, almost $140,000 in energy savings for that school over 10 years. The payback on this, the ROI, was about 3.5 years. So very good for the school on the difference in cost, and they're saving energy continually. A similar look at that, we looked at a 50-story office building in New York City. So this is right in NYSERDA's wheelhouse here for a project. This is a local law 97 approach that we were looking at for a 50-story office building, that are looking at a very large fine if they don't reduce their energy and carbon footprint. And so we analyzed what they have now, which is a COP of 0.75 for the whole system. They basically have boilers, chilling towers, and just raw air being brought into a space where there's an air handler that then heats and cools that air and distributes it per floor on that building. Very high pump and fan power, zero, as far as the COP on the heat recovery, there is none. And so using very high efficiency at 85%, we were looking at a system COP of 5.3 as opposed to 0.75, which is existing. About 80% energy savings on this 50-story building. We did an analysis of that at the time. It was about $1 million a year in energy savings for the building. So this is how very high efficiency ventilation really has a huge impact when you're trying to do electrification decarbonization. To give you a comparison on systems, this is a typical rooftop unit. It's a gas pack rooftop, so it's using gas for heating and it's using DX cooling, electric cooling. And it has a system COP on a year-round basis of about 1. And what you have on the right is using heat pumps and very high efficiency ventilation. As a whole system, you're looking at a COP near 5. So you're using about 20% of the energy for the system on the right as you are on the left. And this has been borne out in many, many projects that we've done where we've saving huge amounts of energy while providing heating, cooling, ventilation for the building. This very high efficiency HVAC retrofits is based on reducing dramatically that ventilation load, as I said, downsizing the heating cooling system, I mentioned at the beginning, because you have much lower heating and cooling requirements for the outside air, you can use a smaller heating and cooling system. So we're reducing the capacity of the heating cooling system. And then it's designed to be really simple. This is a project we did where we took this RTU off, this bottom right picture here. That's where the RTU used to be, and now it's just a small HRV doing the ventilation and the heating and cooling by the heat pump that's on the left. So it looks like this: take rooftop units off, replace it with a heat pump system, air handlers, and a ventilation system. Again, seasonal COPs. There's heating and cooling, 5.6, 5.3, very high efficiency, very large savings on energy use. One other important thing is what we call design for off. These two lines, the blue line is 70% efficiency. The red line is 85% efficiency. That 15% difference has a very dramatic impact on the comfort of the air you're bringing in. And the reason we call it design for off is the box here, this light shaded box, is the comfort zone from about 62 degrees to 75 degrees. If you're bringing air in that zone, then generally it's pretty comfortable. You're not going to be feeling cold drafts. You're not going to be feeling warm air, and it'll mix and distribute into the space very readily. And the heating cooling system can easily then manage it. If you're outside of that zone, in the heating season here, at 70%, you fall outside of that zone at about 43 degrees. So anything below 43 degrees outside, you're going to be bringing in air below 62 degrees. You may be looking at doing post-heating or having to run the heating system continuously to manage that. At 85%, instead of 43 degrees as the point where you fall out of that below 62, it goes all the way down to about 20 degrees here. So anything between 20 and 43 degrees, very high efficiency ventilation is bringing air in at a comfortable level. On the upside here in the cooling, it goes out of cooling at about 87, 88 degrees at 70%, whereas it goes up to over 100 degrees at 85%. So much less use of the heating and cooling system and just running the ventilation without the heating and cooling system needed in a lot of cases. So again, we're system downsized, very low fan power, heat pumps, ventilation and ventilation systems that are using very low fan power reduce a lot of energy. And then controls with demand control, scheduling, and other things are very important to the whole system. And the key here is you can do this with almost any type of building. I showed you a 50-story office building that we were looking to do one story at a time, one floor at a time. We've done, this is a terminal building from 1930. It's a historic building at Boeing Field, King County Airport in Seattle. That's what I showed you earlier, the roof. We've done office buildings. This is an office building in Maine. This is an office bank building in Maine as well. We've done restaurants all over the country. So almost any kind of building can be done. This is the results from some projects we did with the Northwest Energy Efficiency Alliance. So we took, this is the before and after energy use index for these buildings. So here it's 73% reduction. The average is about 70%. This one is that terminal building at the airport, 84%. So that's, you can see, very, very significant energy use for HVAC reductions. Here is the heating cooling capacity that we before and after on those same projects. So we took 46 tons of rooftop units off and replaced it with 16 tons of VRF. So very consistently, we've reduced that capacity by close to 50% or better in most of these projects. This is the exception. It was really a matter of somebody donated them 2 6-ton heat pumps. They still we're at over 80% HVAC energy savings on that project, but they took 12 tons of rooftops off and replaced it with 12 tons. That's kind of an exception. And fortunately, the heat pumps can cycle at, very variable load, and we're able to manage it no problem. So this just gives you an overview of these projects and whole building savings and HVAC savings. So goes from the most at 85% for that airport project. That's that engineering office. The average is around 70%. Restaurants are a little bit harder because they use huge amounts of energy in the kitchen. They have a big hood blowing all the energy out of the building at the stoves and make up air. So they're high energy on their HVAC systems, but still pretty significant HVAC energy savings. There are two restaurants shown here and did pretty well. One's at 73% HVAC, the other at 43. This is a project we did. It's our first project in Portland, Oregon, where we took that 45 tons of heating off the roof, replaced it with 16 tons of VRF. And this is the before and after. One of the biggest takeaways here, and the utilities like this, we took the electricity from 18.9 kBTUs per square foot to 19.1, and the gas went from 32 to 0. What that means is we didn't fuel switch. We didn't shift the load onto the grid, which is a lot of concern with utilities. They're going to get rid of the gas and put it on to the electric load. In most cases, we haven't done that at all. The other thing is demand. We shave this whole demand right off on this project. And this has been very consistent with this. We shift the demand, the peak demand, to the winter time, and very, very limited on impact on the grid. So this is the airport terminal building. Very quick. It was dual deck RTUs, and I want to show you the graphs. Again, electricity went from 76 to 47, gas 45 down to pretty close to 0. They have some domestic hot water, a little water heater for the bathrooms there. But there's demand. You can see demand went from very high peaks up over 120 to the peak at around 60. So cut demand in half on that project. This is the Portland office, 84% HVAC energy savings, 66% in the office. Before and after, same thing. And one of the big takeaways here is that on an extreme case, this is 112 degrees. So this is in Portland, Oregon. They had a heat wave 2 summers ago, and the design temperature is 90 degrees. This is on a day that's 22 degrees above design. This thermostat set at 75 degrees, and it got up to 77, basically. They were able to maintain about 77 degrees, even on an extremely hot day. And this is 2 hot days in a row, and they were able to maintain it inside. So even with, these very high efficiency systems, it can handle extremes on both sides. And this is an office building in New York. Very quickly, we took dual deck RTUs off, replaced with heat pumps and VRF. Starting EUI was 148, ending was 50, with a 66% reduction. And the annual energy savings. This was modeled, and this is typical. It was modeled pretty modestly, and we exceeded it by about 300%. So they're saving in that 71,000 square foot office building, and this is several years ago. Energy prices have gone up a bit. They've saved over $200,000 a year. So that's the model that we've used. It's a very effective combining heat pumps of any form with the very high efficiency ventilation systems can result in a really, really high efficiency system when you're doing electrification decarbonization.
Great. Thank you, Barry. Can you go back a slide? We're seeing a blank screen.
Oh, there. Yep. Sorry.
Great. All right, excellent. Well, thank you so much. If anyone from our audience has questions, please post them in the chat. I'll start us out though. I'm curious about for retrofit applications, the ducting and how you deal with that situation in terms of balancing when you're talking about residential, when you're talking about commercial, particularly with larger buildings like EBC confronts, how you typically deal with the ducting and minimize loss of residential space or usable space.
Well, a lot of the time, if we're taking off on these projects, we've done RTU replacements. We've actually used a curb adapter to take an RTU off and put an ERV or an HRV in its place directly. And then we repurpose that ductwork that used to be for ventilation, heating, and cooling from the RTU is now a dedicated ventilation system. The ducting is oversized, but that means you keep your static pressures low. You may have to use some dampers to, add dampers to manage that airflow to get it to the extremes of the ductwork. But in a lot of cases that's already zoned by RTUs, it's been very effective to just put a curb adapter on, and then the VRF system, the heat pump system, runs through refrigerant lines, or if it's a hydronic VRF system, water lines that go to indoor units that do the heating and cooling. Other cases, we've leveraged the ductwork that was existing with an air handler from the heat pump, and then put in a, call it smaller, more accurately sized ventilation ducting system for the ventilation. In the case of residential, that's the biggest challenge when you have a large network of smaller ducts going to apartments. And that may require some either car dampers, which I'm not in love with, but we have used them effectively in some cases, or dampers just to make sure that the air is distributed properly. But generally, we've been able to repurpose ductwork and keep cost to a minimum and really optimize it. And the results have been very good.
Great. Follow up to that. In terms of the trade-off between heat and energy exchange from a monetary standpoint, how does this typically pencil out in terms of the savings that you get from either scenario? And what is usually the preferable pathway, or what decides that preferable pathway?
What versus what are you?
Sorry, heat recovery as opposed to energy recovery.
Oh, yeah. I mean, generally we go by two things. There's two metrics that we use. One is the type of building. If it's a really highly, densely occupied building that has a lot of internal latent, call it moisture gains, especially in the winter, you have to be a little careful of that, because high humidity in the wintertime inside, that's produced inside with a lot of people, showers, cooking, all that, potentially could lead to moisture in walls, and then you have problems. But for the most part in New York and New England, we use ERVs, energy recovery ventilators, which are recovering both moisture and heat in the wintertime, versus heat recovery ventilators that are just transferring heat between air streams. We want to keep the humidity out in the summertime, especially, so they're effective. And moisture is actually energy. I don't want to get into all the details, but retaining some of the humidity in the wintertime is actually retaining energy as well. So mostly we use ERVs in the Northeast. In the Northwest, where they don't have the humidity factor as much, Oregon, Washington, California, British Columbia, we mostly use heat recovery ventilators, HRVs, versus ERVs in the East.
Great. Another question, in terms of indoor air quality, particularly a consideration post-COVID, what are you finding in terms of your system and how that is addressed the concern that homeowners and building owners have, and how that's typically addressed?
Well, by doing dedicated ventilation, rather than, an RTU, rooftop units typically have a damper that opens and introduces air into that recirculating system where the heating and cooling is recirculating. There's a return duct back to the rooftop unit where it's heated and cooled and then distributed back into the building, and a damper introduces air at that point. A lot of it's recirculated, and I still have thoughts that RTUs doing that recirculation may have contributed to the spread of COVID. They say they didn't, but I'm not sure about that. Whereas you have now decoupled, in effect, your heating and cooling with a heat pump system, and you have a dedicated ventilation system that's 100% outside air being introduced into the building, and then stale air is being exhausted, and it's traveling through that heat exchanger. And as I said at the beginning, the Passive House certification pretty much assures you that there's no cross-flow contamination between the exhaust air you're getting rid of and the fresh air you're bringing in.
Great.
And then filtering, our very high efficiency Passive House requires MERV 13 filters on the supply air, so it's highly filtered air as well.
Great, thank you. For the Tarrytown project that you mentioned and the site EUI of 50 that you achieved, was that only with the Ventacity system, or was that inclusive of other measures that were done at the same time, such as heat pumps, envelope treatments?
Oh, it was all heat pumps. We took, and I kind of call this worst to first. We took dual deck RTUs, which are, big rooftop units that are doing simultaneous heating and cooling and are very inefficient. Big fans, big inefficient fans. They were very old. So we took those off and replaced it with heat pumps, a full VRF system. That was doing heat recovery, so it can do simultaneous heating and cooling into the building with the heat pumps and the ERVs.
Got it.
And that's pretty much the model that we use.
So then the follow-up question is, how does envelope performance relate to this? And typically on a retrofit project, in terms of the performance goals, are you mainly doing just replacement of the mechanical systems, or are you also looking at the condition of the envelope to achieve the highest air tightness and efficiency?
Well, in most of the projects that we have done, it has strictly been HVAC replacement. The envelope hasn't been a big part of it. The law office I showed, the first case study there, the first project we did, they did replace the windows, which meant the building was a little tighter because they sealed around the windows and they had better windows. But the building still, they did door tests on these projects, and it was still considered a pretty leaky building. I think it had 8 air changes blower door test on that building. So when you do a balanced ventilation system, you're not pressurizing or depressurizing, so a leaky building isn't a big factor. But the other thing is, because you're putting in a balanced ventilation system, you can tighten that building up as much as you want. So if you want to do those envelope upgrades, air sealing, insulation, you can go as far as you want, and you don't have to worry about that because you have a good balanced whole building ventilation system. But those results that I shared, almost all of those results were strictly HVAC replacements. The envelopes were not part of the upgrade or retrofit.
Great.
That would only improve your numbers even further.
Sure. Barry, well, thank you so much for your time today and for your insightful and informing presentation. We very much appreciate you providing us this information, and to everyone who attended. And yeah, please tune in the future.
Thank you very much.